Hi, we are now going to learn about a fascinating topic, the Earth's magnetic field. You know that if I took a magnetic needle like this, let us say that this is the north pole of the magnetic needle, and I kept it near a bar magnet like this. Okay, so this is the north pole of the bar magnet, that is the south pole of the bar magnet, and this red portion there is the north pole of this needle. And if I release this needle, what is going to happen? It is going to turn and always points towards the south pole of the bar magnet. This is something that we can do a lot of experiments and see. Okay, so you know that basically like poles repel and unlike poles attract. So this is the north pole of the needle and that is the south pole of the bar magnet, and so they obviously attract, right? So you know that this is what is going to happen. But now what is interesting is that if you take the Earth and you do this experiment, not keeping a bar magnet, just simply hanging needles from different places. Okay, so suppose I keep a needle like that there, it will swing this way. Okay, so the north pole of the needle actually points like that. Similarly, if I keep the needle here, it swings this way. Again, it points towards broadly the same direction. In fact, if you keep it in Spain, again it is going to turn and point towards the same direction. I can keep it in China somewhere, and then again you see that that's what happens. And what if I keep this in Dubai? You see that it will turn like this and point there. In fact, even if you keep it in the ocean, it will turn and point in the same direction. Notice that all of these are pointing there, like very close to the geographic north pole. But if you look at this experiment, you see that these needles should point to a south pole of a bar magnet. Maybe there is a giant south pole sitting there, right? So that was an idea that people came up with, that probably there is a huge south pole, earth magnet south pole, sitting here at the geographic north pole. Okay, well obviously if that is the south pole, then this must be the north pole of this earth magnet, right? This must be the north pole. Now if you notice, this north pole is pointing that way, but this must be the south end of that needle, right? Why is it not pointing this way? That's because the earth is curved. So you have to imagine that this is three-dimensional, and so if this is the line, you have to draw the line like that. So actually, yes, it is indeed pointing towards the north end of the earth magnet, right? North end of the earth magnet. This, of course, you can see directly pointing that way. Here it is pointing this way. If you imagine that there is a curve backwards like that, then it is going to be pointing there. Now, this idea, we can try and understand this a little better by looking at this animation, right? So if you see this axis, that is the axis of rotation. So the earth is rotating like this. And when you talk about the geographic poles, they are actually based on the rotation axis. They are based on the rotation axis. So earth is rotating like this. This is the axis passes through the center. Wherever the axis comes out, like this will be the north pole and that will be the south pole. Geographic north pole and geographic south pole. Now when we say that the earth, if you think in terms of the earth magnet, okay, so let me now consider the earth magnet, and you say let's place it in here. Notice that it is not at the same place as the geographic north pole, right? So that is the geographic north pole, whereas this is the magnetic north pole. So magnetic north we call it, but actually it is a south pole. You know that it is a south pole. Okay, all the needles point here, so the names may be a little confusing. This is called magnetic north because it's close to the geographic north. But of course we know now that this is actually a south pole and the other end was a north pole, right? But notice that these two are not exactly on top of each other, right? There is a small shift. So the actual magnetic north, which is the earth magnet's south pole, okay, that's called the magnetic north, is little bit slightly shifted from the geographic north pole. They are not aligned. Does that matter? Yes, we will learn that this is going to play a very important role in our understanding of Earth's magnetic field. Now, this idea that this kind of a magnetic field exists around the Earth, and probably it is because the Earth itself behaves like a huge magnet, right? That's why we talk about the poles of the Earth magnet. This idea, when was it discovered? Who discovered it? Let us now look at the history of the magnetic field discoveries. The first person who proposed that the earth behaved like a huge bar magnet was William Gilbert. And he proposed this idea in 1600. And he actually didn't go around the earth to map out the earth's magnetic field. What he did instead was to build this little model of the earth. Okay, he took a small spherical model with a magnetized spherical model. Basically, he called it the terrella. Terrella basically stands for little earth. Terra means earth. So this is terrella, a little earth, right? So he used this model and he measured the magnetic field produced by this magnet. And he showed that this was very similar to the magnetic field that you actually observe on the earth's surface. Now, following William Gilbert's idea, a lot of other scientists started to map the magnetic field of the earth, and that allowed us to understand that the earth indeed behaves like this, and it has a very powerful magnetic field all around it. Now, don't go around thinking that this was the first time somebody recognized that the earth had a magnetic field. This was a proposal that the earth had two poles. Much before William Gilbert, almost 2200 years ago, people had already recognized that the earth had a magnetic field. They were using compasses. This was a compass that was used in China in 260 BCE. So you're talking about something like 2200 years ago, right? So basically, all these compasses were used for navigation purposes when people wanted to find direction. But navigation is not the most important use of the Earth's magnetic field. Then what is the use of the Earth's magnetic field? Let us understand it. Did you know Earth's magnetic field is the reason for life on Earth? Without the Earth's magnetic field, there would be no life on Earth. Why am I saying that? When you look at the sun of course gives us light, energy and so on, but the sun also has huge storms like this. And from these storms, it blasts out massive amount of super fast charged particles. We call this the solar wind. Now these particles, as they rush across space, if they directly came and hit the earth, no life on earth can survive. Okay, if these particles came and hit the earth directly, all of us would be gone. Luckily, that does not happen because the earth's magnetic field shields us from these particles. So how exactly does the magnetic field protect us from these particles coming from the sun? Let us try and understand that now. We saw that the sun sends out a huge number of very high energy particles, charged particles. But as they approach the earth's magnetic field deflects them like this. You know that magnetic field exerts forces on moving charges. Now these are moving charges, right? Moving charged particles. So therefore they get deflected like that. And because of the charged particles that are coming from the sun, the earth's magnetic field is not symmetric. It gets stretched out like that on the other side like this. Okay. Now some of these particles, they end up entering the earth's atmosphere near the North Pole and the South Pole. So some of these particles spiral in like that. And when they do that, in the North Pole and South Pole, you end up seeing some beautiful light displays which are called aurora. Now basically the northern aurora, okay, this is a photograph of that. This is near the Arctic. It is called Aurora borealis. Borealis stands for north. So this is the northern lights. Aurora borealis simply means northern lights. This is a photograph taken from the ground. And there is a spacecraft that took a very nice video of the aurora that happens around the Antarctic. So this is in the southern hemisphere. This is called Aurora australis. Australis basically stands for south. So this is the southern lights that happen here. You can see a very beautiful display from space like this. So basically, if you notice this, except for these two regions, most of the particles that came from the sun, they got deflected, and that's what protects the earth. And so this region is called the Earth's magnetosphere. And so this protects the earth from very harmful radiation from the sun. So the radiation from the sun is called solar wind, but that is not the only thing. There is also cosmic rays that come from all directions that also gets deflected by the magnetic shield that we have. So without the earth's magnetic field shielding us, right, from the super fast charged particles, we wouldn't be there today. So the reason we exist is thanks to the Earth's magnetic field. So is it useful? Super useful. What causes the Earth's magnetic field? Is it that inside the Earth there is this huge giant magnet? Well, for a long time scientists actually thought that that was the case. They thought that iron pieces, magnetized iron pieces, somehow got aligned in this fashion, and that basically created a huge magnet-like effect. But it turns out that this is not the correct reason. So today we know a little bit more about what produces the Earth's magnetic field. So suppose I take the Earth and I cut it open like this, you see that the Earth is made of many layers. We live on this outer layer which is called the crust. If you go inside where you have a lot of this lava, right, it's called magma. So that is basically the mantle. So this is the mantle. So that is called the upper mantle. If I go further in, that is the lower mantle. Inside that, this portion is the outer core. It's a liquid core, liquid iron core. And finally at the center is this solid iron core. Okay, so this is the solid iron core and this is the outer core, which is the liquid iron core. Now, at the center of the Earth, the temperature is very high, 6,000 degrees. Now, iron melts at 3,000 degrees. So this should not be solid, right? It should be liquid. But it is under enormous pressure. So though the temperature is really, really high, 6,000 degrees is the surface temperature of the sun. Okay, at the center of the Earth, we have the same temperature. But though the temperature is so high, because of the enormous pressure, the core at the center is solid. That's why it's a solid iron core. Okay, most of it is made of iron and nickel. But just outside, the pressure becomes lesser, though there also the temperature is high. Because the pressure is lower, this basically becomes a liquid iron core. Okay, so this is the liquid iron core, and that's very important because liquids can move. And because of the Earth's rotation, and of course there's a lot of convection because this is very hot, heat starts flowing out, right? So because of convection and Earth's rotation, the liquid starts moving. And not only moving, it is moving very turbulently, and so that produces a lot of twirling flows. And think about it, iron and nickel, they are conductors. So when you have a conductor moving in a magnetic field, Earth's magnetic field is there, right? So in that magnetic field and a conductor moves, what happens? You know, according to Faraday's law, it produces an EMF and therefore an induced current. And so because the current, right, because of the movement of the iron and nickel liquid core, so what happens there is that it produces current, induced current. And induced current will in turn produce a magnetic field which strengthens that original magnetic field. And of course, some of these magnetic field lines will pass through the solid core as well, which is also iron. And there it will realign the magnetic moment of that solid core. And so that will strengthen the magnetic field further. The energy for this is produced by or comes from the movement of the iron and nickel atoms in the liquid core. So that's what gives you the energy. But basically this is like a self-reinforcing process which is called a geodynamo. So the geodynamo process, Earth's rotation and heat convection, it creates twirling flows of the molten iron and nickel in the outer core, liquid core. That's very important. The solid core cannot move, right? That cannot move. So the liquid core is very important. So the movement in the liquid core of iron and nickel, that induces, right? The magnetic field induces a current in that liquid core because it's moving. And so that induced current in turn produces a magnetic field which then sustains and strengthens the original magnetic field. So this entire process, self-reinforcing process, turns out to be quite a complex one. So scientists are still studying it. We don't fully understand it, but we know that this represents the reason for how the Earth's magnetic field gets produced. We have already seen that Earth's magnetic field protects us. To understand this a little better, let us compare the Earth with our neighbor Mars. Mars is about half the size of the Earth and it also has an iron core. Did you know that a long time ago, Mars had an atmosphere and also had water? Basically two ingredients essential for life. But today it doesn't have an atmosphere, no water either, right? So what happened? How did it lose its atmosphere and water? That's a very important story that we need to understand. Now, remember that the iron core of the earth has two parts. There is a solid iron core and there is also a liquid iron core. And the central portion is very, very hot. And the heat from the center, right, from the core, it slowly radiated out, right, through the surface. But now because Mars is much smaller than the Earth, it radiates the heat out much faster. And because it's losing heat much faster, the core temperature dropped. And 4 billion years ago, the temperature dropped so much that it lost its liquid core. Everything became fully solid. So Mars today has only a completely solid core, and that happened about 4 billion years ago. Whereas the Earth still has a liquid core. It has a solid core portion right at the middle, but then after that, surrounding that, there is a liquid portion. Why is the liquid core important? Because the liquid part is where the movement can happen, which then produces induced currents, and induced currents will then produce the magnetic field. So once the liquid portion, liquid core of Mars basically was gone, right? It was completely solid. So then that means there is nothing to move, and since nothing is moving, you cannot have a magnetic field. And so basically Mars lost its magnetic field. So what if it lost its magnetic field? Remember that there is huge number of charged particles coming from the sun, solar wind. And the solar wind, because now there was no magnetic field, it basically hit the atmosphere of Mars and stripped away the atoms in the atmosphere, blew it away effectively. It also evaporated the water and then blew away that water vapor. So today, Mars has neither an atmosphere nor water because it did not have its magnetic field. So the reason we have an atmosphere, we have air, we have water, we have life is thanks to the Earth's magnetic field. So our magnetic field shields us from the solar wind and protects our air, protects our water, and protects life on Earth. I hope you have understood how important Earth's magnetic field is.